Oh
spaceport.
wow, this is fully filled.
Like the heart, you think of it like a lead screw base. So it
etc. How many cameras and like how will float? The first stage will float post.
It's called the object adjustment module.
Of the rocket, basically, what you see here is all the.
You can go inside a little bit. You have an opening here. So.
I won't go in. I'll just put the camera in. Oh wow! This
Propulsion system, mostly like strain gauges. Stage 1 test fired one.
okay.
Yeah. So this is what we call is like actuator loop simulation, and this is, you see, these are the cases, you know. So this is the so this is the tested Raman 2 engine, you know. So this is
minus 18.
Yeah.
So we'll go in.
Hey man. Hi.
Welcome. Hello.
Hi, welcome.
Really awkward. Let's go in.
Yeah, let's go.
We'll. Oh
Spaceport.
wow! This is fully filled
Yeah.
compared to our last visit.
Yes.
I think last visit we could record like calmly because there was so much space.
Yeah.
Now we'll have to like wrangle around.
Yes.
Which is a good thing.
Lot of stuff.
Oh wow! This view.
So all the rocket interstages are here now, undergoing electrically integrated checks. Full-fledged checks, what we call a phase 3 of the integrated test we have. This is the last leg of tests in Skyroot before we ship things to the airport.
So you were saying nerves of the rocket are here, like.
No, yeah. So basically, propulsion system is already at the site. It's more like the heart. You think of it like the heart. And 3 stages, first 3 stages of the rocket are already at the spaceport. And here we have the brain, which is all the avionics, which makes all the decisions as the rocket. As you know, rocket is fully autonomous. Before liftoff, the automatic launch sequence, and then takes off continuously autonomous until the payload is ejected into orbit. So you need a lot of decision making on the ground, during the flight. And so that all happens through the avionics systems. So which is more like the brain. Then we have the nerves, which is the harness which connects all the electronic sensors. And sensors are like the eyes, which tells where the rocket is. We have the main inertial measurement unit. Here we use something called a ring laser gyro, so which is like super sensitive, and it's very precise. It gives the location of the rocket, and we have so many sensors which tell more about the rocket. This is the first flight. Also, the whole purpose is also to get as much data as possible through all the sensors. The sensors are like the eyes, harness is like the nerves, and you have the actuators which move the nozzles, more like the muscles. And you have the brain. So all that is here, and we integrate all of them, and we call it like integrated checks. And these are the final checks before we send to the spaceport, and then we'll start assembling them to the propulsion systems which are already there. We've been there for quite some time, and then we start assembly integrated operations, and then it goes to the launch pad, and then assembly on the launch pad, and then takes off.
So let's take a walk through.
Yeah, let's go. Can I point here?
Yes. So these are the actuators that actually move the nozzle. Basically, every solid propulsion stage has this flex nozzle system, which is the thrust vector control of that of the solid propulsion is done by this actuator.
So if I can point out, this look like screw. They are moving a screw.
Yeah. So it's like a lead screw base. So it has an electric motor, which turns the lead screw. The lead screw will move up and down, micron, level accuracy. And then you have 2 actuators. So basically 90 degree you have 2 of them, and essentially you can move any 360 degrees. You'll have all directions you can move, and it typically can move up to 7 degrees, and then it will steer the rocket as it goes.
So you don't need huge movement to make a lot of turn.
Because the thrust is very high. So only to get the enough control authority, you just need a slight deflection to overcome any kind of aero disturbances that we can.
Yeah, so basically thrust is very high, and also the center of gravity is also quite high, right? So when you have an offset in the nozzle, so you'll have enough torque for the rocket to move. And generally, even if you see the angle of attack of the rocket, is generally should not go beyond 4 degrees. So generally very low angle of attack it goes. The rocket is generally like mostly aligned and it goes along with the flow.
I guess you have to model that whole like flexing of the rocket when it's tilting also.
Yes. Like basically, there's something called 6DOF simulations we do. There'll be a rigid body model and there'll be a flex model. So all the control systems will be tested in the rigid body model, and same thing has to be validated in the flex, taking into the flex traj of that system, and that way we validate things on system, and same thing will be deployed on the mission computer.
So do you assemble the whole rocket and try to flex it? How do you know that your models are
is working
for the hardware?
So basically that's the first flight for, right? So first flight you'll not be able to simulate exactly like how it is on the ground. So we have something called a vehicle model. This is all physics basically. What is the inertia? What is the mass? How much angle will create? How much torque? The entire control system is modeled. Everything is modeled. So basically everything we have a vehicle model. Think of it like a mathematical model for the vehicle. That mathematical model for the vehicle will not be exactly how the physics is going to simulate in flight. So there will be some variations, but generally these variations are not so high that it will cause something which is completely unpredictable. Right, so this is good enough for designing the entire vehicle, and then it will almost predict how it is in real life.
So the dispersion will be well within the bounds in which the control system of the rocket can take care of basically.
Okay. So would you have sensors along the walls of each of the stage to measure relative flex from the top to bottom?
Yeah, we do have something called bending mode accelerometers, which will sense from the first flight we'd actually know the truth of the first bending mode and the second bending mode of the vehicles. And so all that instrumentation is through the telemetry we get down to the.
And if you're talking about the flex of the nozzle, we have something called you can see these these two. They're nothing but sensors. So they tell you how much angle the nozzle is moving. These are called mirror imaging sensors. So you'll have one opposite each actuator. As the actuator pushes, you detect exactly how much it is rotating. So these sensors give feedback to the control system for controlling the nozzle in the precise orientation which you want as the rocket stays down. So that is one sensor. You have so many sensors. You can see this. What is it? You can see this sensor. So that's more like a microphone. It's like an acoustic sensor. So it measures the sound as the rocket takes off. You have almost close to 160 decibels. I mean, for example, a human ear would just burst at that sound levels. And so just to measure how do you. So we also build an acoustics model for the entire rocket, where the sound is what, because the sound will actually go and hit the systems inside, hits the payload inside the fairing. It's very important to have a good prediction of that, and then as per that we test it on the ground. For the first flight we test it with some assumptions, but then you check the flight results and then you fine tune it.
Okay, we'll talk more about this the fairing, the sound and the fairing.
Oh yeah,
part,
sure. Yeah.
So this is the what part of the rocket are we looking at?
So all of these are interstages, what we call interstages. So if you can see the top part, you can see the pseudo blueprint of the rocket, and all the checkered part is essentially the solid propulsion stages, and all those stages are already in the launch pad now. So what you see here are the interstage structures, which contain all the electronics, all the electrical harnessing systems, all the plumbings, everything else other than the propulsion systems. And these are electrically integrated and checked. We can simulate, do a simulated input profile of all the rocket trajectory, and we can make the entire electronics in the rocket experience as if they're going in the flight, and how will they behave. So this is an electrically integrated check of all the interstage subsystems.
This is the same, what they call hardware in the loop test or HL.
It is more of a rocket electrical integrated test. Hardware in the loop test, we will come to that, where we do a closed loop run simulations, and this is where we do that. That is one part of the activity we do in this. a closed loop simulation run. But there is separately there are test beds for the closed loop simulation runs. We'll show you as we.
Like for example here, right? So between these two, we'll have a 10-meter long stage 1. Which has like a propellant already filled in.
So first
and so basically this blue one is what is below the stage 1, and this is what is above the stage 1. And you can see the separation interface. You see this interface 1, 2, 3. There's this separation. There's 6 points of separation. So this whole is one single part which is called the stage 1, and then it separates along with the first stage propulsion.
Okay.
So basically the propulsion system, stage 1 propulsion system gets sandwiched between these two structures, and all the brain for running that is this, and interconnected with the mission computer. The mission computer will come from the top, it gives the signals, and then you have an execution module here, you have electronic to move the actuators, you have a control electronics which gives it the signals, high power signals. You have like huge amperes of current flowing in to move this actuators, right, all that. So basically it's an independent system which will separate after the first stage completes. So in real, it sandwiches the stage 1 in between. It's almost like 12 meters long. Almost half of the rocket is between these two.
From what I'm picking into these holes, all these pipes and all, they are for the separation.
They are for the separation system. And so here we use pneumatics. Traditionally, like separation systems use pyro systems. So pyro systems are like imagine like gunpowder, like firing, and then that creates some actuation which will separate, or you have an RDX squad which cuts the rocket and then is separate. So here we use something called pneumatic separation system, which is testable and reusable. For example, here you see like we have done a vibration test of this, and then we tested the separation, and then only we are going for flight. So exactly the full circuit will be fully tested before flight, and the same thing will be used in used in flight when we take off.
Those pockets are where the separation mechanism will come, and those mechanism is kept safe separately because it's not safe to expose that metal for long time for environment. So there's a safe storage package. Okay. And once we go to the launch pad, we'll assemble all the mechanisms back.
Okay. I'm sure there must be some depth to how the battery has to be charged before the launch, how there has to be discharged. A lot of depth to talk about. So coming to storage, so you all will also have some storage like strategies for your solid rockets also, right? How long you can store them and...
Yeah. See, ideally, like, they can be stored for 10 years, and that's one of the advantages of having it. You can produce as much as you can, and you store them and use it whenever you want, whenever the customer wants. And so right now, they're already in storage at ISRO for a few weeks now. They're waiting for, the rest of the rocket to come in and start integration. And so I mean, like, there's no, in fact, all the materials used in building the propulsion stages, they're all like, they have that life of several years, almost close to a decade, which can be stored. But generally, we store for a few weeks, sometimes few months, and then get to flight.
I guess y'all don't have that issue because it's a single segment, right?
Yeah, it's
if
a single
it was
segment,
multi-segment and had to be separated, now you have problems with storage.
Correct. Yeah, no, even multiple segment also, you store them as separate segments, and then you have to assemble them at the launch site.
So basically pre-launch there will be additional assembly work. The advantage of a monolithic propulsion stages, you can just integrate and directly integrate with the interstages and go. The pre-launch assembly work will be minimal if we have a monolithic solid propulsion stage.
Okay.
That's the only advantage.
No, there was one issue with GSLV once where they had assembled it.
Yeah.
It went into, they disassembled it.
Yes.
Then again reassembled it and... So, I guess you all won't have that issue. You all can take your time to get this thing ready.
Yes, that's right. And we don't have joints. I mean, like the propulsion system is monolithic. So, there's no assembly, disassembly, issues there.
This is smaller.
Yeah, second stage.
So second stage ones.
Okay.
So the second stage comes between these two. As you can see, this wire, what you see here, is the one that goes around the second stage, on top of second stage, externally on the white tunnel of the rocket, basically.
That external pipe like thing.
Yeah, it's called a white tunnel. So tunnel for like moving the pipes, because you can't route pipes inside the propulsion, because you have 3000 degrees centigrade high pressure gas. high temperature, high pressure gas, right? So you have to route it over the surface of the propulsion stage, and then for that you have tunnels. That's why you see the projections on the rocket. So they are basically to run these wires from top to bottom, and here you have the length of the stage 2, and that side you will see like a huge pile of wires, because the length of stage 1 is almost 10 meter. Now we exactly simulate the same wire which is going to fly, connect everything. You see all the signals are going well, they're all communicating well, and we check each connection, everything, as per flight, integrated and tested. And we also give flight profiles, so we simulate failure scenarios. We simulate like, if some ground system fails, whether it will react, how the whole system will react. We simulate extreme scenarios of, how the rocket can get into in the mission, and then we see how the signals are going, how the rocket is reacting, all that we do it, yeah.
Okay. So this test is not just for the test for the rocket, it's just for the ground system also. Basically, the ground system software we develop, how it interacts with like all failure scenarios. If one such bug happens, if a hold parameter is supposed to raise a hold, whether the hold logic is working well, it's a combined test, not just for the flight hardware, but also for the ground test system, so that once we go to SKYROOT, things will work plug and play, is the target.
So how much learnings were from this rocket? Because there also you all operated ground systems and all of this.
You're talking about Vikram-S?
Yes.
Okay. So Vikram-S was a suborbital single stage rocket. So where most of the systems like the propulsion system, the carbon fiber composite structure, the thermal systems, all the TTC systems, telemetry, telecommand, everything were way back developed in 2022 for this, and same thing we are able to utilize here. Basically, that know-how of and ability to the trajectory estimation, like it was like a textbook launch where with our estimation and the launch has exactly matched. So our ability to do the trajectory analysis and carbon fiber based solid propulsion stage, having the flight heritage for it, also was a great advantage.
And also we also tested some avionics, so we call it like the transponder, which will which will tell where the rocket is. We put the mission computer, we had a lot of sensors, we had a lot of materials, the thermal coating, which will help prevent the rocket to heat up.
Same one we're using here.
Yeah, in fact that is extreme, because you have extreme vibration, extreme acceleration, you have extreme temperatures, because it cuts through atmosphere very fast, right? So with all that we got built a lot of confidence on the materials we use, the choices we made, and that data has been used in a lot. For example, if you see inside the rocket is all black. You see like it's all carbon, it's all carbon composite, and outside you see you see a thermal coating which takes very high temperature. It can go even like 1500 to 2000 degrees centigrade, and doesn't heat up inside. Now outside can be 2000, inside you can touch it. So it will be so effective in insulating the heat not to get into the structure, so the internal structure can be like within its temperature bounds, and do it. And all these materials also have been tested in the Vikram-S launch.
Okay. So from the engineering side, how I think you have explained the sensors, etc. How many cameras and like how?
So we have multiple cameras. There'll be 2 external cameras and there'll be few internal cameras which see the stage separation activity from internal. There are maybe around 5 to 6 cameras will be there around through the length of the launch vehicle. But our only constraint will be like due to telemetry bandwidth, we have a restriction. We don't have the luxury to transmit all camera data at once. So based on the event, the appropriate camera will be switched and the correct appropriate camera will be streamed at the correct time, basically. So the switching logic is on board, and it will take care of which camera will stream at which event.
Can we see the stage 1 falling into the sea? Will it be able to stream all the way down?
You can see the separation. And after that, because the camera will be on the next stage,
Interstage.
so the stage 1 only separating part you can see, because both are in different trajectories.
Okay.
Because it will go on its own ballistic trajectory. This will be the thrusting away. So
but stage 2 at least we should be able to see some.
No, stage 2 also the same. Stage 2 will be in a ballistic trajectory, and after separation.
So
and the rest all will
parent computer is all the way up in the
all
stage.
at the top. Yes,
Stage 4.
Yeah.
So once a stage is separated, even there is a camera on that stage, there's no link and no communication from that stage. Okay. So it is the ongoing stage is the true vehicle we care about. And all the data that comes from, active data that comes from also is only from the ongoing stage. Any spent stage that is expended is for the C2. Okay.
Future experiment then.
Yeah.
Independent camera, S-band, TTC.
Yeah. And then like you should have a complete set of avionics systems which can support the, you know.
Yeah.
And but Vikram-S we had footage, right? Because everything is independent in a single stage.
Yes.
So we could see like, you know, almost as close to
Splashdown
we could get the
we
footage.
got telemetry even till 2 degree elevation, which is very, below 5 degree people won't honestly expect, because it's a huge sea.
Yeah.
Till 2 degree elevation angle we got perfect, almost close to Splashdown we got the telemetry.
Okay. Yeah, you all will have to have your own Navy.
Yeah.
I mean, coming to Navy, do you think this will float? The first stage will float post?
No, I mean it'll once it splashdowns, right? You know, slowly it'll sink. Because if you see, like it has a large, all the propellant is consumed, and the nozzle is essentially an opening, right? So it's slowly, it's like, you know, imagine like putting a cylinder on water, on a tank, on a bucket of water. Slowly it'll sink. You know, water will enter, you know, air will bubble out.
Right.
Slowly sink, but you can actually build systems such that it can float. I mean, like if you want to make it float, like for example, the space shuttle boosters, you know, you can make the system float. Yeah, with parachutes, orienting in the right direction, it can float.
Because such a big composite booster, no one has flown yet, right? All the boosters that have fallen have been aluminum or metal casing.
Yeah. Mostly it will be steel, you know, and in India all the big boosters are metallic. And now we will be the first composite, you know, which will fall, which is en route to space and is falling in the sea. And it's
maybe Sri Lanka, or again another news. Sri Lanka found some booster.
No, but in fact, like, you know, this is a carbon composite. It's heavier than water. You know, its density is like you know, almost 1600 kg per meter cube. Which is like more than the density of water. So by nature also this material, like, you know, sinks in water.
Only PLF might sink.
Yes. The PLF might float. Yes, because this is like very light, because of sandwich hardware. Yeah.
So in the future maybe we'll see something. So those look like latches I see on airplanes. This one.
Yeah, that's actually one of the external facing camera where it will come.
Oh, okay. So this is interstage of stage between?
These are between 2 and 3.
Between 2 and 3.
And it also has, you know, it also has the roll thrusters. So we have like 4 3D printed roll thrusters, which will fire. You know, you can see this here. We just closed it because we don't want it to contaminate. You see an elliptical shape here. Yeah. So this will have like a you know, firing. You know, it is basically a scarfed nozzle. So it will create fire tangentially, and we have 4 of such. So if you want to rotate the rocket anti-clockwise, these will fire, and if you want to rotate clockwise, these 2 will fire. Right. So the thrust will create clockwise, anti-clockwise. And they'll be in pulse mode, like, you know, continuous pulses depending on the orientation, because you need roll control. The rocket has pitch yaw roll control. So pitch and yaw will be given by the nozzle and the thrust vector control, and the roll will be given by this until the stage 2. You know, and after the stage 2 separates, we have very small thrusters because the rocket is very light. So we have very small thrusters on the final
stage 4.
What we call it as orbit adjustment module. And then there we have like little thrusters, you know. So here you have gas thrusters which will fire.
Okay.
Then so basically they are like valves which will open and then expand the gas.
So we are now looking at, this is stage 4 into stage 3 and
4. Yeah, it's
4
between stage 3 and 4.
Actually, if you see the in flight, they are actually very tightly close together. They'll be bonded. So but to electrically integrate, to keep them separate, it was very difficult. So we had to turn it, and because the harness slack will be very less, because it's supposed to be together.
Correct.
But to electrically integrate, it has to be positioned in a clever way so that we can, that slack is enough just to connect it electrically, and then we test.
The wires itself must be adding a lot of, must be few kilometers of wires, no?
Each strand, if you put, of course, it will be multi-kilometers. I think better we can calculate over the tool itself. I'll get that metric done. But yeah.
What are these wires? Is this Ethernet or what is it? Like from hardware?
There'll be single digital, there'll be multiple communication buses is something, but all instrumentation sensors are just direct analog sensors that directly go to the respective data acquisition modules. So most of the harness you see is because of the instrumentation sensors, multiple sensors going to the respective data acquisition module, and the other buses where the communication buses will be there. Those will be very small. Generally, either like multiple communication protocols we use on the launch vehicle. Those will be most of the harness weight comes from the instrumentation sensors to data acquisition module cabling.
Okay.
So as we proceed to the subsequent launches, that is where actually most of the saving and payload improvement also comes from, because as we reduce the instrumentation, because first launch is generally heavily instrumented, just to get as much data as possible, and the only primary purpose of the first launch is to get as much information as possible.
Yeah.
So, and as we get more confidence, we can optimize on the amount of instrumentation that goes into the launch vehicle. Thereby, it not only reduces the mass of the sensor, but mass of the harness that goes from the sensor to deck. And that's one of the key payload improvement initiatives that generally taken up in any launch vehicle as they mature. Basically.
So just going back to there, those large cylinders in between.
Yeah.
Those are the pressure fed.
Yes. So basically those are for the fuel at oxidizer, which will be pressurized because we just need few kilograms of fuel for this, for the roll control, because it's operating in few pulses throughout the mission, and but then here it needs to, the requirement is that it needs to fire instantly. You have to fire instantly. So we use hypogolics, which just like the moment fuel and oxidizer come, it creates a pulse, and then it can orient the rocket in the roll direction whenever we want, however we want. So basically, it's very precise roll control it gives.
Those are COPVs. Those.
Yeah. So you see the blackish. Yeah, correct. Those are COPVs, which have like high pressure gas, which will push the propellants in these tanks, those long tanks, and then from there it goes to it goes the engines. Both you have fuel and oxidizer, and then it fires.
So I see there is a remove before flight pull tag inside many of the stages.
Yeah.
So during assembly, how it will work? Before they stack the stage, they have to activate some systems.
Yes. You have to remove the systems because basically one of the key things is contamination. So because you'll be working in bit of a dusty environments sometimes, and people will keep walking around, sometimes they touch, etc. Right? So we don't want contamination to happen. So we plug it wherever some open ports are there, we plug them so that they don't contaminate. And then we have some closures. You see, like for example, this is a fully 3D printed engine, which is basically a Raman 2 engine, which will power the uppermost module, which is called the object adjustment module. And so this one, for example, we closed the output. So we don't want like any dust entering the engine, etc. From the bottom side. So we keep it closed, and last minute we remove this cover. And then we have certain valves which can be activated only if you pull out a pin. Even by mistake, somebody gives a command, that valve will not get actuated because it's mechanically locked. And for that also we remove the pins. And even for the ignition of the solid fuel stages, you have a safe arm, which has a mechanical pin. And then that means even if you give a wrong signal, the rocket will never ignite, because there's a mechanical pin which will hold the the system to pass the pyro train to ignite the igniter. Right. So like that we have a lot of mechanical locks, safety locks, which we have to just remove before the stages are integrated.
So all of this you have to discover as you make, right? Because I was thinking from engineering point of view, had to there are few software engineers who are responsible for the assembly software as one stage is getting stacked on each other. Yeah. Checks are happening.
Yeah. No, I think simulation is a pretty long activity, and we have to simulate all failure scenarios, which is left to one's imagination typically. And so like the software is one really challenging part, where all scenarios we have to imagine before and then like build it and build the systems, hardware also aligned to that.
So, just to give a glance of the scenarios we test, because in solid propulsion sometimes the actual performance in flight will be slightly higher or lower than what you expect. So, actual time of separation will vary, but and actual separation is initiated by sensing the acceleration. Like as we go very close to the minimum threshold acceleration, so the thrusting phase of the rocket is ended, and then you sense the threshold and then you separate. But the threshold sensing can happen at any time, depends on the performance of the stage, how well it performs. So actually, to sense the threshold, we'll have some valid time windows in which we sense the threshold. There'll be a start time and stop time, in between which we actually sense the threshold sensing acceleration. So we just want to test whether those are working fine also. So sometimes we remove the IMU from the loop and test whether it is sensing, because it doesn't sense at the end of the terminal time it has to sense. So all the cases where all the fail-safe error prone corner case scenarios that has been coded also has to be triggered in the integrated runs, which will nominally never get triggered if things go well as nominal. So all these things happen in the electrical integrated test and the checkout integrated test. That's why the number of tests we do also will be very long, because we need to validate all the corner cases, not just for the flight but also for the ground system.
So coming to that cutoff condition, PSLV had read a paper for the third stage. They were having this whole tail of thrust situation where they have to wait 120 seconds for the tail of thrust to, because the tail of thrust is significant that the stage can come back and hit the stage 4.
Correct.
Do you have that issue with stage 2 or 3?
So we do this a healthy time we wait generally. There's a healthy time we wait after the cut off of a stage, like after one stage burns out and the next stage ignites, just to take care of this tail off. But it's well estimatable currently, because a lot of tests we have done on the ground, static tests. Everything is well predictable and will be well within the bounds.
Okay. I see a lot of these black boxes have your branding on top of it. A lot of custom hardware looks like.
Yeah, everything is designed in house from scratch, and then in fact these development cycles are very long, because these are built to reliability. So they should not have any kind of failure modes which can put the machine in trouble. So it's like extensively well designed, all most failure modes addressed. And then we have a test campaign at every stage, and then we have you assemble all the package, and then you again test across all environmental conditions, and then we integrate, and then like now for example is integrated checks. Once we integrate, you will have new problems, right? For example, as a system things may work, but as a system of systems it may not work, right? So all that we simulate, and then we test them, and then ensure that this is good to go.
Okay. Stage 4 is the most different stage, right, compared to everything else. I think it's more consistent. Here from this side itself, there seems to be a lot of plumbing besides the engine.
So, because this is the orbital adjustment module we call, because this gives the large, the bare minimum delta V it's required for the launch vehicle, and it is mainly to compensate for the over performance or under performance of the solid propulsion that within its bounds it might create. So all the fuel in it is mainly because of that additional delta V for the injection, and also for the guidance. What we call is something called guidance margin, where we have some extra fuel, which in case, like even in the worst case of all solid propulsion stages, all the 2-3 solid propulsion stages underneath underperform, so that we don't get enough delta V they nominally would give to the launch vehicle. This guidance margin should be able to give this extra delta V and be able to inject the payload in the orbit. Right.
Okay. I mean, I think we know each other since 6 years?
Yeah.
5 years, 6 years. That time this central engine thing was not there.
Correct.
You all had the outer
engines.
What happened? Why did you all move? Because now I see outer engine. Now I remembered. What is this outer thing? And
No. Originally, what happened was we had only a single engine. Okay, we called it Raman engine. Okay, So that engine was supposed to give the roll control, whatever roll control engines which we talked about, and the same engine we wanted to use for pitch and yaw control of the stage 3. So that means, like, let's say the stage 3 will have a fixed nozzle, doesn't have a flex nozzle, and then the pitch and yaw control will give it through pulses from the orbit adjustment module. And then after the third stage separates, then these 4 engines will burn continuously. So we wanted to use it like
both for the control and for the main thrust.
I remember we talked
yes,
about
yes.
this.
So that was we found it very elegant design at that time. But then after a lot of simulations, which we realized that it's one thing is very risky, and second thing is that it was also costing us payload. And because we had to put the fuel for control of the third stage in the uppermost module, which is causing payload loss. As you go up the rocket, you have we call it the payload ratio. The payload ratio becomes 1:1 in the final stage. That means 1 kg. If you add something, you lose 1 kg of payload. So you add a lot of fuel to control the third stage. So that did not go really well. Then we changed this architecture. This is much more complex architecture, but it's more reliable architecture. So we put a central engine, and then here also we did a full payload analysis where the central engine can be gimbaled like the first 3 stages. You can have actuators.
Those are actuators.
Those are not actuators. They're just like assembly now. They'll be they just to make it fix, lock it rigidly to the stage. So we could have, for example, those could be actuators which will move the engine, or it could be like small thrusters which will, because the thrust of the upper stage is very little, because as you go upper into the flight trajectory, you need less thrust to actually take the payload. Because you're separating out all the mass as you go up stage 1, stage 2, and other things. So this is the final stage. The engine thrust is low. To control it, you don't need much thrust. So you added small thrusters called Raman Mini. So these are like mini thrusters which will pulse and control the central engine in this stage. And so these thrusters also are used for separating the third and fourth stage. Like for example, after the third stage separates, you need to create some sort of distance between them as quickly as possible. And these are the things which fire so that they don't collide. The third and the upper stage, they should not collide. So they give that separating velocity.
Basically, it actually de-risks the tail of thrust concern you mentioned. Any residual tail of thrust that goes beyond the prediction also, this push that ongoing stage gets will de-risk that.
Yeah.
Also, you need to settle the fuel, I guess.
No. So here we come with a different kind of system where you don't need, there is no there's no movement of fuel inside. We contain them with a bladder, and then like it, the bladder pushes it continuously, the fuel, and it's just a very special design which has like a metal bladder which will work, which will bend as it's a different kind of expulsion, right? So that pushes the fuel. And it is always pressurized. I mean, you don't need that, the velocity or the acceleration, not velocity, the acceleration to push the propellant down.
Oh, this is new.
It's called the positive expulsion device.
Okay.
More like, it helps push the propellant always. And so typically in liquid fuel systems, we have a problem called slosh, because the fluid starts moving. Just imagine like on a truck, you put a water tanker filled to some height, and then you move it, the water keeps moving here and there, and then like it causes trouble in the movement of the truck, for example, right? So this is a slosh which is happening inside, the water keeps moving. So here in a positive expulsion tanks, you don't have that slosh effect, and so slosh is eliminated, and also like it's a very positive expulsion tank where you don't need acceleration to keep the propellant down, right? So this is and this we have to test multiple times in multiple ways to prove its expulsion efficiency, and it's also a very, very unique special design which we have for doing that. This is well proven now.
Okay, so coming this side, you have this large round. These are fuel.
These are the tanks. These are the fuel and oxidizer tanks, and these are the ones which have the expulsion device inside. So they have a bladder which will be pressurized by the gas. And it's always it has positive expulsion all the time, and it ensures that fuel is always at the bottom. And then typically you have opposite sides will have the same propellant, either fuel or oxidizer, and so that the CG is balanced out.
Okay, now we are at the business end. What is happening here on the... What is this adapter? What is faceplate? What is this called?
No, this is the avionics bit. This is where this is the brain of the rocket. Basically, what you see here this is all the key OBC, the onboard computer. What we named our onboard computers as Raman. So that is the key computer that actually computes everything. Basically, all the commands, all the guidance, navigation, and control algorithms run there, and that is the one that commands the subsequent actuators, the roll control thrusters, everything in the respective stages. So the telemetry, the tracking system, everything that needs to function, that is critical for the functionality of the rocket till the end of rocket journey, all the electronics will be there in this avionics bay. And on this, we will get one more plate, which will on top of it, where the payload deck will come. So the payload deck is currently not here. On this, it will
be mounted on this. You can see those interfaces. It will be mounted on this, and then on which the satellites and other payloads, will sit on it. And then the fairing comes around this, so it protects the, it protects the whole satellite payloads and this part of the orbit adjustment module. And then it separates the moment you cross 100 kilometers so that when you don't need the fairing.
Even these plates look like carbon fiber. You all are all in on
all in all carbon. I mean, they're super light, very good to manufacture. Of course, you need a really good capabilities in processing them, and I think we have mastered that piece, and we've got very comfortable with using carbon fiber for various applications. And in fact, now we say anything metal we have to replace. Eventually, it has to get replaced with carbon composite.
Yeah, very few places in the country are skilled at carbon fiber because it's a very human process, right? I mean, you have automated some of your stages, but such things, so you need...
Yes. So it's a mix. I think some processes which you use, for example, for the propulsion systems, it's heavily automated. We have a 4-axis robot which does all the winding, and for the structures, it is manual process skill based, but that also can be automated. So eventually in volumes that also will be automated, and then so that way when we know which process to do what, and then do you put, and also carbon composite is more it's like additive manufacturing. You add layer by layer, you put the layer where you need the strength, you put the direction which you need the strength. It's super optimized, it's and it's really good for. That's the reason if you see the whole aerospace space industry is moving more and more composite, and so that's super light. For example, if you see regular steel, carbon composite is 20 times lighter than the regular steel, and it's far lighter than even aluminum strength is not high. The strength is even stronger than the strongest steel, and then very light. Density wise 5 times lighter than steel.
So yeah, a lot is happening here. As an engineer, just panicking looking at this. So many things have to work together in sync.
Absolutely,
No tolerance for one error here.
Yes, and that's the beauty of rockets, right? That's why it's called rocket science, where everything has to be perfect actually during that mission, right? And then it's generally said that even if you have a successful mission, you just succeeded by a whisker. There's some things which could have just gone wrong, but you managed to make things right in that particular mission. So you have to be on your toes for every mission, every time, and typically the most trivial and most unexpected things go wrong. So the attention to detail required is extremely high. In every system, in everything, every part, every system, every subsystem, every wire, every plumbing, every fastener, the attention to detail is required is super high.
That Japanese H3 rocket, that adapter
has failed, right? And that is unimaginable, and it's just broken, and the satellite fell off in between the mission, and then and it also if you look at the reason, whatever happened, I think the fairing separation happened, and then that triggered this one, and then that had some impact on the propulsion system. A lot of things stacked up in the failure.
Right.
So typically there are also some things like few things going wrong and adding up, stacking up. Individually, if one of the things go wrong, probably the mission may go right. But multiple things going wrong and stacking up at the same time also cause failures, many times.
Yeah.
So
I think we can talk about the fairing. It's a huge fairing.
yeah. So
Not even fitting in this.
yeah. So I think we can, all three of us can fit in.
Easily.
Yeah, and yeah.
How tall this is? 4 point?
It's almost close to 4 meters.
4 meter how tall? And this is like whole composite.
All composite.
Can I go and put in the camera?
Yeah, you can go inside a little bit. You have an opening here. So.
I won't go in. I'll just put the camera in. Oh wow! There's a lot of things happening inside.
Yeah, I mean this is one of the most complicated pieces of hardware in the rocket. Because it has to protect, so it gives us structural protection, it gives acoustic protection,
Maximum thermal stress it also.
maximum thermal load is on it, and then it also has to separate, and separation system is most complex. So you have to separate like a clamshell. It is vertically you have to separate, horizontally you have to separate, and very very precise sequence. And this is probably one of the toughest. Probably you might have seen the YouTube video of we tested
Separation system,
payload fairing separation, and so this is again a fully testable system. We separate the actual fairing which is going to fly with the actual systems, actual plumbing, everything to what is going to fly, and then we test it, which is also very rare. So that also gives the confidence and reliability in the flight. So when you put things together, high chances of working. You never know until you have the launch, but you just increase the probability of success by being able to test exactly how it is going to go and fly.
So then, just slightly going back to the Raman, even there, for the valves, what you did then? Did you use pyro valves or again reusable valves only?
No. There it's reusable valves.
Okay.
And so we have high pressure solenoid valves. So it's like extremely high pressure. We took enough time to develop those valves, and they should not leak at extremely high pressure. It should work reliably, and we build those valves, and we also have an abort system. If things go wrong, we can switch off, on. So we have like fully automated systems to take care of the entire stage in extreme scenarios.
Okay, because the NVS satellite issue.
Yeah.
Maybe that could have been prevented if they could have tested, because it's a one-way pyro valve once fired cannot be reused.
Yes. And from what I read, it's like maybe two systems did not work at the same. On the same mission. It's like even if one redundant, there is redundancy, and both did not work or something of that sort. I'm not sure how true that is. That's what I've read somewhere.
How do you, if you were in place, how do you approach this problem? Because now if you add another redundancy, you need to test that redundancy, and then you go into this loop of adding systems.
Correct.
So generally redundancy, not on that particular subject, the redundancy itself, as you rightly pointed out, has its own complication, brings in its own failure modes to address in general. So we need to deal with the concept. Redundancy is not just one-step solution to solve any critical systems. Ensure that it will only give you some comfort, but it will add n more failure mode that you need to address.
So the best way is to build one system which will just work. It just works, and also for small vehicles, you don't have the luxury for redundancy as well. Because you add more redundant systems, your payload goes down, and you have to optimize here. You have to optimize in grams. For example, if you have a huge rocket, so you can optimize in kilograms, sometimes tens of kilograms, sometimes hundreds of kilograms also. So you have the luxury to add a lot of redundant systems, and then if things go wrong, other thing works, right? But there also, if you have redundancy, you have a new problem to solve, where the redundant systems also have to address all the failure modes. But still, there is luxury to think of redundancy. Here, there's very less scope of thinking of redundancy. So you have to build a system which will work, which have to work.
And you might have seen, once you put the camera, you see a lot of acoustic blankets, which is, as you pointed out, which is essentially for foam covered blankets, which will protect the payload from the harsh external acoustic sensor. It will give easily to 12 dB attention.
So air hitting this surface is making the noise.
Yeah. So what happens is that as you take off, right, the plume, it creates the noise. So for example, as the rocket lifts off, you hear a big sound, right? So that is nothing but like huge sound, and that sound comes and it hits the fairing, and then from that it transmits inside because it can't absorb the fairing. The fairing can't absorb the sound, and then it goes inside and hits the satellite. So that is like so that is very detrimental for the satellite because satellites are very sensitive to vibration. So what we do is that we add those. You saw those aluminum. Those are foils, aluminum foils. But inside you have those foam which absorbs the sound. And so much good portion of the energy gets absorbed here itself. So that inside you don't feel that much vibration as it is outside. But without these systems, you will have a heavy vibration inside.
On SSLV D1 flight which failed, there were a few issues they pointed out of the FDI system and all kicking in. One of them was they had to reinforce the stage for vibration. The stage 4, they had to dampen it more. So this plate that will go on top of this is slightly dampened, or the points are dampened.
So not here, because see here the suppression systems which are using are as I told, it's pneumatic, and it is very low shock suppression. So so it has gas, and then like it has like some proprietary mechanism which separates smoothly. It doesn't generate a huge shock. So when you have a huge shock system, you should have the safety systems to absorb that shock typically, and that to some extent you can test on the ground, but to a large extent you may have to check it in the flight itself. But but generally we create a robust system which will typically work. So there probably they might have tested it, or unexpected shock has come. What could be the reasons, I'm not aware, but there could be like a large shock then.
The shock saturated the inertial system. And then that spiraled on top.
Yeah. So hopefully, I mean, like our shock is probably will not cause any issue because the shocks are low. But see, these are the things which you can only see in a flight. Right, so there are some things which you will not be able to test on the ground. For example, when you do separation system, you only have 2 of the interstages separating. So you don't actually simulate the entire rocket above it. Right, and there could be more sensitive elements in other places which could get affected by this shock.
Yes.
Right. So what we do is that we typically measure the shock, and then we simulate whether this can create any issue in further upstream or further downstream of the rocket.
And we define the qualification criteria for those modules so that whether it can take this
much shock, and we test every module with shock. So we have a shock, we have vibration, we have thermal, so we have various environmental conditions which we test all the electronics, all the sensitive systems in the rocket.
Okay. What are these holes?
Those are like vent ports. So for example, as the rocket goes up, outside is vacuum. Inside is atmospheric pressure at the time of liftoff, right? And this rockets is like typically like we rainproof the rocket so that nothing goes inside. So it's typically like it's a contained box of volume of air inside. So what happens is that as the rocket goes up, inside is 1 atmosphere pressure, and outside it can become vacuum as the rocket goes up.
It's a bomb then.
So it's like a 1 atmosphere bomb, which is very we don't realize it, but it's. You put 1 atmosphere and then you add the area of it. It's pretty large amount of stress on the rocket. So we have to release that. We have to release that pressure. So we have vent ports which slowly releases that one, and we design the entire system with some differential because it's not like completely. You can't put very large vent ports, because you have to put very large vent ports. You have like very large cutouts in the system with the all structural. The structural integrity gets affected, etc. You have to be as minimal as possible, and slowly it has to vent out and equalize the pressure inside and outside. And so it will have some differential still, but we design the structures for that disassembly. And also very unique design where gas will come out, but water cannot go inside. So this is some system where like for example, even if rain falls, even though there is a vent hole there, water doesn't go inside. You have some. This design in such a way that water doesn't go inside.
There's an adapter which will take care of that. But the gas can come outside. So it's so those all nuances has to be taken care of
in the launch, and also the location is also like very well calibrated. It's the most efficient venting happens there. Right. So at that location, so there is like a pressure distribution on the entire payload fairing, and then like the best venting what we require will happen at this particular location.
Okay. I mean, coming to nuance, since you're talking about rain, carbon fiber is conductive, right? That must have created a lot of hassle with the whole circuit thing.
Yeah.
But also lightning, how do you model all that? How do you model all that? Like,
Yes.
First part of the carbon fiber is conductive, but once it comes into a matrix in the resin form, it's very complex. Like if you put one strand to one strand, if you put multimeter on one strand of wire, it will be conductive. If you just offset it,
because I've seen people while building drones, they've shorted their drones.
Yeah.
Because that connectors on the frame connected to each other.
Yeah.
If it digs in even little.
Yeah. So that's why if you observed, you might have seen a lot of copper tapes inside. So that's basically to distribute all the static electricity. There is no pileup of charge, anywhere in the entire vehicle, and everything is connected. So it's like connected and distributed. So we take care of the electrical distribution through that.
And about the lightning, we are launching from the first launch pad. So it has its own lighting towers.
In flight?
In flight, there's no part to discharge. If at all a remote chance of it acquires charge, it has to stay on the vehicle.
Okay.
So you might have seen like some launch vehicles.
Russian rockets.
If you nothing will go wrong. It should work. Yeah.
Okay. Also, when PSLV is on the FLP, I've noticed it has AC ports like this. AC umbilicals.
Yeah.
And so you'll also have.
AC, correct.
I don't know if it's AC.
That is that.
Cool
That is
air.
that umbilical. It supplies like neat cool air, which can keep the systems cool inside. And it has very controlled air, which is continuously it has to put. That is the adapter is just closed now, but you'll have an umbilical there which will connect to the launch pad and will give continuous fresh air which continuously purges through this.
So all those testing also will be done first time, right? Or with FLP,
how
umbilicals are connecting?
So we have done trials there, and then
all the interface definition, everything is tested. Trials also have been done. So with the actual umbilical, we will be testing.
So that all interface checks we do before, because we don't want surprise in the last minute.
So have you taken a very payload adapter umbilical approach versus taking from the back?
So that's right. So you're talking about electrical umbilical or the
electrical
AC?
As well as fuel?
Yeah, so electrical we have done something different, so you don't see any hanging wires in our rocket, because electrical umbilical is from the base. So it's just like call it a sit-on umbilical. The rocket sits on the umbilical and comes from the bottom to the top. So we avoid that separation, as the rocket goes up. Only cooling will be there, and we have a good supply of cool air, from the system, and then it separates as the rocket goes up. Basically, so that particular separation of the electrical part we have avoided, and it comes from ground top.
Okay, that is nice. So most of the integration testing can happen in the vehicle assembly building itself.
Yes. So in fact, what you see here, right? It's almost all electronics, every electronics, every sensor, all come together, and then like you test. Except there are some sensors which are mounted on the propulsion system, mostly like strain gauges. So that will be tested only at the at the launch site during the final integration. But most of the other things are tested here, because this is the main critical system which will continuously be tested. We have even those pressure ports also here tested. Whatever pressure ports which measure the pressure of the main propulsion system, they're also put here and tested. Right. So here it's a fully electrically integrated checks. Right. So everything is here. So it's like, and then you transport them. Some during transportation there could be some risks here and there, because things are moving, shaking as you transport. But they will be still less than what they experience in flight. So they all will be rigid. But then so after going there, we still again check once again so that everything is intact, and then we integrate with the actual propulsion stages, and again we do final checks. Then we take off. So good thing is that it's all testable. I mean, like you test on the ground and you do it.
So I think that is not spoken about it. I mean, you'll have to design jigs for each of the stage for transport.
Oh yeah. So that's a very specialized, because we have to transport it,
We have to handle it.
so sensitively.
So you can just for handling the PLF, we need to have the handling tag, handling hooks. So the payload fairing has to be designed to be able to for the handling also. So
Yeah. Sometimes many interfaces or like many structures are designed for handling. For example, the stage 1, right? It comes horizontal. Everything is done horizontally, and then for the launch pad, it has to be tilted up.
Okay.
So it has to be tilted up. The structures at the bottom or all joints should take the tilting loads. So design considerations during when we design stuff is all this handling loads are very essential parts, inputs into the design.
Yeah, I've seen them raise the cryo stage of Mark 3, and there are one pivot at the bottom of the stage and one at the bottom. Both are together moving.
Synchronized to move up.
Yeah, and when I interviewed Somnath sir, he mentioned the challenge with horizontal integration because the whole ring could flex a bit.
Yes.
And so you have to pressurize it and then raise it, and just a whole circus you have to do.
Yes. So there are like pros and cons for every kind of assembly. And then here this is our stage 1 test fired one.
Okay.
So this is like the first static test motor case, and it was successful in the very first attempt. And then now the actual one which is going to fly is already at the at Sriharikota, and it's waiting for the other stages to come for integration.
Okay, and what are these then?
Yeah, we'll come there.
Yeah. So this is what we call as like actuator loop simulation.
This is part of the like in-loop hardware in-loop simulation. This is one of the hardware in-loop simulations where we pull the actuator out of the simulation environment. The vehicle will be simulated, but the actuators will be out of the simulation environment and in the real world. So all stage 1, stage 2, stage 3, all actuators with actual flex seals, the flexible systems and the nozzle that actually mimics the actual nozzle in terms of the mass and the inertia, basically. And this, with everything else will be in a rack where all the mission computer, the control electronics that control it, everything will be in a rack, and we do a closed loop simulation as if it's flying. And then actual deflections with actual load conditions, and we match it with something called onboard in loop simulations, which we do just with the onboard computer outside the system. So whether just pure software simulation and actuator simulation, those results should match well. So all these validations, like as much as systems, like there's some other thing called angular motion simulator we have, where like we put the IMU, the initial measurement unit, outside, and we actually give the rates of the launch vehicle, because we can't emulate acceleration. We emulate the rates in the angular motion simulator, and from the sensor output we take in, and there we do the closed loop simulation. Every hardware in loop simulation should identically or as closely as possible to match with the only software simulation, basically.
And then this is, you see, these are the cases, So this is a test fired stage 3 and
so
stage
beautiful
2.
These strands look.
Yeah. So this is like really art coming together. They're super light, and they have to be so precise. And in fact, we have to write the code for manufacturing these the codes of the machine, which will do this winding. Built from scratch by us. So we build the entire software stack for this winding, which will give the least mass. And because it's a little bit complicated system where like the openings are different, and it has to come under the fibers slip beyond certain angle, and they have to be properly wound in a proper fashion. And also this is again no tolerance to any changes. It has to be very precise. So this is something which we mastered, and so far everything we built has worked well.
Yeah, I'm experimenting with carbon fiber rod. I told you the same part can be built with twice the resin.
Oh yeah.
I mean, if you don't squeeze the resin out properly, and if you don't pressurize it from outside, so it's a very skilled thing.
Yes, it's a
building with carbon fiber.
Yes. So that's why I think there's a lot of processes upgrades. Like for example, to avoid squeezing, we can have pre-pregs, top-pregs. So they're pre-impregnated with a very precise amount of resin. Right. So those can be used to make it even lighter, and then more controlled. So you can remove the skill part from the equation there, But our like is like we've mastered this how to do these things, and then it's like very cost effective and very quick to manufacture, fully automated almost. And this is for the stage 1 because stage 1 is too long, so there we build a jig for it. So you have a dome behind it, very small dome, where you can apply a little bit of pressure, and then you move the nozzle. You just imagine this is the size of the stage 1 nozzle, but of course this is only a simulated nozzle which is made of metal. The actual one will with carbon.
Okay.
Yeah.
We had seen this last time.
Yeah.
This is that nozzle.
Yeah, so this is the nozzle picture. You see the bottom, so the dome at the bottom, that's a chamber, pressure chamber. So there we simulate the chamber pressure of the actual propulsion system. It can go up to 100 atmospheres. And then with that pressure, we move the nozzle, actuators and all we test as a first step. Then we go to actuator loop simulation. Then we, then we assemble the system into the flight.
Okay. I think we are coming to a tail end, business end, tail end.
Yeah, so these are all fixtures for like simulating the actuators.
Basically, for a load test, basically what you see there is essentially actual real load, where you pressurize, you have the actual nozzle, actual flex in the system. Here to the mimic, we have spring system, where every time we need not go to the pressurized equipment, we can to test the actuators in a load setup. This is the no load fixture for the no load testing setup. This is a load testing setup for the actuators.
So basically all steps. First we test without load. Then you iron out some issues are there, like fix it there. Then you go to with load. Then you fix the issues there. Then you go to the actual system with the actual simulated nozzle and the flex seal. And then there you clear it. Then you go to flight. So this is all like in few days, the step-by-step process to accept it for flight.
Now the glass is frosted. Last time it was not, I think.
Yeah. So there's a lot of important material inside.
Right. I think we have come to the last section, that is adapters.
This is all for the next flights. Future flights. So they're all like we'll get into integration soon.
You had lifted one of this last time with your hand.
Yes.
This one, I think. This one.
Yes.
It's so light.
Quite light.
This looks like some cool hardware.
Yeah. So this is the tested Raman 2 engine. So this is what was test fired. And here you can see like the plumbing, right? It's all 3D printed, so you don't have joints here. For example, here there's no joints. It's all 3D printed in one piece. And then here you have channels inside, and from this, the channels it will cool, and then it goes finally to the fuel will go in one direction, oxidizer will go in the other direction, and then it fire inside, and including the nozzle also 3D printed.
This is. So, just one very niche question.
Yeah.
This is this laser sintering process, right? Metal 3D printing.
Yeah.
So, doesn't this powder fill this?
It fills it, but we'll extract it out.
Oh, it's a.
Yeah. It's a
but then this
opening
is closed,
pipe,
right here.
Yeah, but still finally this is all connected.
Okay.
Right. So finally fluid is passing through this. In real also everything is connected.
Right.
You have these channels. So you have a process of removing the powder. So
okay, because I see that laser sintering, it first compacts the powder and then, so I would guess it's very compacted inside.
Still we can extract it out.
Okay.
Yeah, and also there is also design for additive manufacturing. So you design in such a way that even sometimes powder can be extracted easily. Okay. So that way I think this is all solved problem now. And this is the injector.
That is that side.
This is the Raman 1. This is Raman 2. So this is where it fires and creates that. This is the scarf nozzle. It fires and creates. So those are the two valves, solenoid valves, which will on and off to create the propellants. And here is the same.
This all looks simple, but this is like art in its own. The whole valve.
Yeah, in fact, it's probably more complex than the engine.
So they need to react quickly, otherwise the delay in the valve is actually the delay we are adding to the controlling loop of the launch loop. So basically, this delay directly contributes to how much time we take in the closed loop control. So the faster reaction solenoid valves will have, the better control we'll have with the vehicle.
And then you ask the valve, right? So this is a high pressure solenoid valve. So I mean this replaces the conventional pyro valve. So this is on and off. It's a system which uses it switches off as a solenoid valve, and like when you give current, it opens and closes it. And so that is the high pressure solenoid valve used there. And then this is the engine, this is a beautiful engine. So you have to.
It is beautiful.
Yes. So it's and also in fact like these smaller engines have their own nuances. Right? You have very less propellant to pull. And then like you have to be like thermally so precise, and then like it has to cool it so efficiently. The channels has to be designed so perfectly. You can't have any kind of errors in printing the channels. It's super sensitive, and then now like we have got comfortable in designing the regeneratively cooled systems with extreme requirements.
This is the first.
First cryogenic.
This is 4 years old.
Yeah, to be even 5 years old. 5 years old.
Then this is the next.
Yes, next version, and then it's just going bigger and bigger. And then you can also see the channels there. You see the channels, how the fluid flows inside and cools the chamber.
Oh, they are very visible here. Very small.
Yeah. The very small, intricate channels. For example, if you want to simulate this, you will have to have multiple, parts welded together. You have to machine them, you have to weld them or brace them, or like there's like so many joints out there. And these are all jointless kind of systems.
So you can't X-ray metal, right? How do you see what you can X-ray metal?
Yeah, you can do a CT also.
They don't get absorbed or.
No.
So you have to do from all like a CT scan basically.
CT scan is nothing but
like a all direction
rotating
X-ray. Yeah, rotating X-ray. And this is like the even much more bigger upgrade. So it's like you keep upgrading with the observations and make it better and better and better. So this is Dhawan 3, and this is also successfully test fired. And so nowadays I think like the engines we go to test bed and fire it in first attempt and come back. So even like models are very very built, simulations are all very intact, and the design is pretty robust, and the attention to details is also like learned over time.
This is all pressure fed, but this cryo one so far.
All pressure fed. And we'll also be firing the pump fed ones.
Electric pump.
Not electric. We'll have like a regular turbo pump.
Gas generator.
Yes. Not gas generator. Probably we'll share the cycles later on. But yeah.
I think that.
This is a freezer. This is a walk-in freezer you see there.
minus 18.
Yeah. So it stores the carbon prepregs. Which we extend the life to several months so that you can use. Without that, it will start the polymer starts cross-linking.
Naturally curing.
Oh, you're right.
Yeah. So that's where it is.
Crazy, man. Like, I've seen Skyroot go from like just an idea where you were pitching, you had just left ISRO, you are just like, to this is like insane.
Yeah. It's pretty complex stuff. Than what anybody can imagine typically, than even what we imagine. So it's literally rocket science, and a lot of attention to detail required, and the talent density required to build such stuff is crazy, and the kind of scenarios you have to imagine, and then you have to build the systems imagining those scenarios so that they don't come. Requires a lot of thought, and then like every system is complex. Every system in itself, and when they all come together, they have to work, and they have to work in that 10-15 minutes of the mission really well in the actual environment, and you can't test everything as in flight, because the actual flight cannot be simulated on the ground to the fullest extent. You can only test as much as you can. And you can't keep on testing also as much, too much, because then it becomes a very, very long, very long cycles of development. And it's pretty exciting, super exciting engineering.
And this is just one of your facilities, right? You have another huge facility.
This is the smallest facility. So we have
other one is closed down, which we had recorded last time.
So that we moved that's too small now, and then we have moved all the equipment to our new facility, which is Infinity, and that facility is more than 5 times of this size. It's the entire.
This is already very big.
Yeah.
So
And,
I think maybe like a lot of installation of plant and equipment is going on. It'll be a perpetual work in progress facility for this year, and like because a lot of improvements we will be doing to it, and it will be fully operational with its maximum capacity. Hopefully before the end of this year.
Yeah. And we have a few labs here also. There are like some vibration testing happening. There's thermal testing happening, and then so we have machinery which can cut the fiber into different shapes. Because typically like we lay, because it's all additive manufacturing, carbon layups. So we basically lay up in the shape of the stress distribution. So stress distributions. So you can actually add material where it's absolutely required.
Right.
So it makes it super light. And so that requires different types of processing, different types of skill set, different types of learning curve to build it, and the equipment, of course, which you choose, and also that also has to be calibrated with the material. Right? So it's a cycle in itself. And in fact, all the structures you see there, they're all structural tested. We subject them to the stress which is simulated in the atmosphere, and then everything went perfectly, everything worked. And now we are started integration. The integration is over, and then now we are doing integrated electrical checks. Now we are sending the whole. Now it's a it's the last day we are here with the hardware. So now we're going to ship all of them one after another in next few days, and they'll be in Sriharikota meeting those the heart, which is the propulsion system, and then we start assembling as modules. Then take to the launch pad, stack it up. It will be a historic takeoff for the country.
So you're in integration hell officially now.
Yes. Yeah. And,
so important question now.
Yeah.
2.5 years ago you said in 6 months.
Yeah. Okay. Yeah.
When is the launch?
See, so the only reason why we took 2.5 years is because that time we thought it's 6 months. And if that time we would have thought it is 2 years, it would have taken 5 years probably. Because see, here there are a lot of unknowns. That's why it's called rocket science.
And there's a famous joke also. Like we are doing this not because it's easy, because we thought it's easy. And it's not. And it's not as easy as.
It's not as easy as it should, and that's how we have to put all efforts to make it as quick as possible. And physics will beat us. It's always battled with physics every day, and you'll see. You'll see surprises which you never imagine. The most trivial things can go wrong, and whenever something goes wrong, like for example, there could be some spurious signals, some packet losses, in the data signals. There could be some component not working. Sometimes lead time of any component to replace itself is very high. And sometimes you have to reduce the risk. When you see that the margins are low, you probably have to go with an alternate design. Sometimes you have to change the designs. Right, so all these come out only during testing. When you test it, you really know the limits, and from that data you have to extrapolate whatever you couldn't test in the flight environment, and then you have to make the necessary changes, and there is cycle time for building that, and it's a super complex, exciting electric process of building a rocket, and so now we are very close. So now we are moving the rocket. All testing is more or less done. And hopefully there are no new surprises at the launch site, but definitely there will be, because it's the first launch. And but what we did is we tried our best to simulate all possible scenarios here itself, so that we don't get surprises there. But still, they will get some unknown new surprises there, which will fix it there. So they could have some delays. So it should definitely happen from now in a couple of months. It looks very likely. But let's see.
Take your time.
No.
Yeah. I hope the first one is successful.
Let's hope for the best.
Yes.
And
thanks for coming by.
No, thanks for inviting actually.
Yeah. Thanks.
Been long.
It's always pleasure to have you, and all the tricky questions you ask. So it's
I just conversation.
It's pleasure to answer them. And
I think once the energy matches, it's fun to talk.
Yeah. And it is always fun. Engineering is always really exciting.
The nuances, especially
the
small
nuances
things,
are so much, and in several thousands. Like you can write a big book of the nuances involved in rocketry. But everything is attention to detail. Everything. from materials to propulsion to structures to software to like the hardware, the electronics hardware, everything. So this based on all things coming together, separation system, right? So it's a system of systems. It is so complex that you have to get all the physics right,
Yeah.
and then fly, and then actually you can only test in real only when you fly. So this is the first flight. I think we'll get as much data as possible. So we understand the weak links, and typically we hope it's unknowns, so that we addressed all the known unknowns at least, and then we get the data in flight, and then keep improving. And the improving journey is like keep on all flights. Even continuous successful flights, you still have improvements, which keep stacking up. Keep getting better and better.
Yeah.
That's why the world has very few launch vehicles operational.
Yeah.
You need to undergo that curve of development and improvements on a consistent basis, and build that heritage and keep building that heritage, and then world will have more access to space.
Yeah. Excited for the first launch.
Yeah, thanks again for tuning in, and I think now we'll miss this space, and literally I'm having withdrawal symptoms of after our last launch. Took so much time to get to our upcoming mission. So now we're really excited to go back to the launch pad, launch site, and do the activities there. It'll be a very memorable moment for us, and of course very major milestone for India's space sector.
Yeah, also quite the thing, right? You're going back to your ex-employer to launch a rocket from their launch pad. Crazy, crazy moment philosophically.
Yeah, to some extent it's a lot of nostalgia, because I used to work a lot on the second launch pad, because I was working on the LVM-3 program at that time. So it's fantastic to work on the launch pad at those heights, to sit on the hardware and work. It's very nostalgic. And now we are working on the first launch pad. It's getting prepared, as we speak, for the launch. And then ISRO is, as we all know, fantastic organization. They have the best teams, best facilities, and in fact they are one of the very, very good reason for success of a lot of our testing is we never face testing issues. Typically test facilities also cause a lot of issues. That we don't see at ISRO facilities, because they are all streamlined to the detail. And then now even the launch pad is meticulous. The moment you get into those facilities, everything is meticulous, everything is calibrated, everything is planned, everything is documentation is perfect. So you don't, at least from their side, it's all this is perfect generally, because they've been through these cycles quite a lot, right? So it's really fantastic to work with them, and they've been enabling so well. I mean, they built such a fantastic facilities and expertise to support, so that all we're getting access to that, thanks to the government policy and reforms, and in space especially. In space works like a startup, right? It's super fast, super lean, very efficient, forward thinking. And I think blessed with such an organization which runs as faster than us to make things happen and move the space sector forward. I think good that all things are coming together, all stars are aligning.
Yeah.
And very important milestone for India, and then also for the space sector, because we need more and more launch vehicles, more access to space. And this is also for us, it's also a first step, right? We had a baby step with Vikram-S, now first major step, and then this will be the foundation for the bigger steps going forward. Yeah. So great again. Thanks for coming.
Pawan, Bharath,
so,
thank you.
Thanks for coming.
Thanks.
Yeah. Thank you.
Special thanks to Jem Sharma, Vutla Chaitanya, Shaunak Perni, Kumar Akhil, Munu Babu, What's New, Vidyasagar Ronaki, Vipul Vaibhav, Yash, or Nitin Gopinathan.